Hello everyone, hope you are doing well. So in the last class we learned about the matrix algebra, and today we are going to utilize those knowledge about matrix and matrix algebra to find the representation of of a group in general. So this will continue for a few days. So how to find out the representation of a group and how to utilize that, and then we will see, okay, there are different types of representation, different ways you can find the representation and all these things. So let's get started. First, to find out how to form a representation of any given symmetry operation. Now, one important application of matrix algebra is in expressing the transformation of any given point or the collection of points. Okay, so it can be a single point as well as the collection of points which defines a body in space. Okay, so we will use this particular property. Okay, so this particular power of or ability of matrix algebra to do this transformation of one particular point or a collection of point in belonging to a particular body in the space. We will use this property to have the representation. Now, that's what we are going to do. So, if this matrix algebra can do that to any particular point, then it's understood that this symmetry operations can be represented by a matrix algebra. It's simple to understand, right? Because symmetry operations does the same thing. It as if it transforms one particular point of a body to another, giving an indistinguishable structure. And matrix algebra also does a very similar thing. It takes one point and transform it to another point in the body. So I should be able to express all this identity or reflection symmetry, inversion. So this should be small I here, small correction here, and proper axis of rotation or improper axis of rotation. All these symmetry operations can be represented by matrices, and that's what we are going to do now. So we will start by the element identity and the following identity operation. So in case of identity, what we have that we have no change as such, right? So if one does nothing, you say that, okay, I have performed an identity operation, correct? So if there is a point in a body whose coordinates are x, y, and z, after the identity operation has been done on that particular point, what is the configuration or what is the coordinate of that particular point? It is x, y, and z. So in order to have a matrix that will resemble this transformation, that is x, y, z, which is normally written in terms of column vector. So as you can see on your screen, so to start with, I have an x, y, z column vector which denotes that particular point that we are considering here, and then after doing the identity operation, my point becomes, or rather remains, x, y, z, which is also represented by a column vector. So since there is no change of this particular point, so it will remain the column vector here, and column vector having the same elements in the same order. So I need to find out a matrix which will help me going over to here. So essentially this is nothing, no change has happened. So I should have a matrix which is capable of doing a multiplication with this column matrix or the column vector. So I should have the same property which we discussed in the previous class, right? So it should have definitely 3 rows. Okay. So if it has 3 rows, then it can have multiplication, and in this particular case I should have 3 rows and 3 columns. So in a sense I should have a 3 by 3 square matrix that can act as the identity operator, and it should not change any of this x, y, and z in the column vector. So only way I can satisfy that if my matrix is this, that is all the diagonal elements are unity and rest of the elements are 0, which is nothing but the identity matrices. So this was very easy, right? So in order to represent an identity operation, symmetry operation, which can be acted upon any given point, any general point whose coordinates are x, y and z, that particular matrix will be an unit matrix, okay, or the identity matrix, okay. So very easily we can get the matrix representation for this identity operation. Now let's move on to other type of symmetry operations. So we will start with reflection next. So reflection symmetry all of us know very well now. Now if I select a plane of reflection which coincide with the principal Cartesian plane. So what I mean is, if I have a Cartesian coordinate system, okay, so x, y and z. So in this Cartesian coordinate system I have an x, y plane, okay, I have x, z plane, I have y, z plane, okay. So I can choose, if I am given the freedom, then I can choose my reflection plane of reflection to be one of these xy or xz or yz planes which are natural to any Cartesian coordinate system. Then reflection of any general point has the effect of changing sign of the coordinate measured perpendicular to the plane while leaving unchanged the two coordinates whose axes define the plane. So what does that mean? So let me explain this by using the board. So suppose I have my coordinate system given like this. So this is my xz plane, okay, and this is my xy plane, and this side it is my yz plane. Now suppose I take any of the given plane to be my reflection plane. Say for example I take my xy plane. So xy plane, how can I depict it? So this is my xy plane, okay, this is my xy plane. Now I have any general point here, okay. So let me say its coordinate as x, y, z. Now what will be the fate of this reflection operation? See, since the reflection plane coincides with one of this natural Cartesian coordinate plane, that is xy here, so none of this x and y coordinates will change, correct, because this will remain at the same place, x and y, but the z coordinate which is perpendicular to this plane will get reflected. The other two will remain unchanged. So after reflection it will go somewhere below the plane, okay. So there this point will have coordinate x, y and z. I said it will be reflected. So I know right now I have the point where the z coordinate is in a positive z direction, correct. So now this z will go downside and it will have a negative coordinate. So it will be exactly inverted because reflection will take you equal distance on the other side of the plane. So you have minus z, okay. So that's what we wanted to mean, and you can do this for if you choose any other planes. So if you choose, say for example xz or yz plane to be your symmetry reflection plane, you can find the same thing. So one of the coordinates will become negative essentially, okay. It will change the sign, but the other two will remain unchanged. So now we are ready to find out the matrix of matrix form for this sigma planes, okay. Now henceforth we will be talking more general way, that is we will talking about say sigma xy, sigma xz, sigma yz because we will be taking any general point on the space, and we will be dealing with this Cartesian coordinate, 3 Cartesian coordinate. So for one particular point I have 3 Cartesian coordinate system. So we will define our symmetry operations also in terms of those x, y and z. Okay. So very often you will get to hear that only c to z, c to x, or sigma x y in that way. Okay. So now one more thing I will mention here. So if I can write this position coordinate in terms of a column vector, what I can do, I can write x, y, z, correct. So now when I have this sigma x, y, okay, so I will probably write it like sigma x, y. If I operate on this one, what's happening, x and y remaining same and z is becoming negative. So you have x, y and minus z. Okay. So this is my final matrix after I operate sigma x, y on this column vector. Okay. And it's only the sign which is changing for one of the elements of this column vector, and rest of them are remaining completely unchanged. So in order to find the matrix form for this particular operation sigma x, y, I have to do something, that we have to form a matrix which makes this transformation from one column vector to the another column vector. So here if you look at on your screen, you can see the the matrix representations for sigma x, y, and this will be pretty easy for you to understand. Since x and y, they are remaining unchanged after this reflection operation, I will have the elements as 1 in the diagonal for say the element 1 1 and element 2 2. Now the third one, that is the 3 3, that is going to change the sign of the coordinate z coordinate. So that should be a negative sign. So it will be 1 1 minus 1 in the diagonal, and obviously the other off diagonal element will be 0, because if it is if the other elements has some value, then I will not get back my this column vector. Okay. So similarly you can figure out what will happen to the column vector when we have a sigma plane along x z or y z planes, and the corresponding matrices form also you can easily figure out. And you can see, if you compare this 3, you can see that the position of that negative 1, the element negative 1 is changing with respect to the the column vector. As we change the column vectors, this is also changing. Okay. So you can just see the 1-to-1 correspondence between this position of this matrix element and the corresponding change here. Okay. So similarly you have a change in sign here for the y, and accordingly your matrix will bear a negative sign for this particular element here. Okay. So it should not be very difficult for you to form any such matrices, and suppose you would have to do it for more than 1 points, you should be equally able to do that. Now let us come to inversion. Inversion is another one which is not too difficult. In case of inversion, what you have, you take any general point on the body. If its coordinates are x, y and z, then after the operation is done, that is after the inversion symmetry operation is done on this particular point, each coordinates will get inverted. What does that mean? That x will become minus x, z will become minus z, y will become minus y. So you get from x, y, z column vector to minus x, minus y, minus z column vector. Okay. So here this minus x, minus y, minus z, they are represented by writing x bar, y bar and z bar, that we have come across in one of the previous lectures. So in order to invert the sign for each one of the column vector, but not changing its say x character. So like I am going from x to minus x, but I am not going to x to y or x to minus y. So x is remaining x, only the sign is changing. So in that case, this will be exactly similar like the identity matrix with a negative sign. What does that mean? The diagonal elements will be -1, -1 and -1. That's what exactly is shown here. Okay. So this is true for any representation that you can form using this 3n coordinates. So now I said, like, here I have only one point, so I have 3 coordinates. If I would have, like, 4 or 5 points, so I will have 3 into that 4 or 3 into 5 such coordinates. So accordingly your matrix size will go up. Okay. So for 3 coordinates, I have 3 by 3 matrix. If I would have like 2 points, I would have total 6 points, because I will have x1, y1, z1, x2, y2, z2. So my matrix would be then 6 by 6 matrix. Okay, and I will have 6 diagonal elements, which will dictate the fate of this points at the starting point to the ultimate structure. So that's about the inversion symmetry and its matrix representation. Now we will look at the proper rotation. This is one of the most important and vital. So let's look at this proper rotation and how can we find out the matrix representation for proper rotation. Now here also we will take a general point having the same x, y, z coordinate, and we will have another assumption, that is the proper axis of rotation that we are going to deal with, that is along the z axis. So which means if I have same coordinate system again here, then my principal axis of rotation will be along about this axis. Okay. So I will say this is, say I have some Cn, C as Cn z. That will tell you that the Cn axis is along the z coordinate of our Cartesian coordinate system, and then we will do all the operations. So now one thing is pretty clear from this assumption, that if I take any general point here on this in this space, say I take a point here which is P having x, y and z coordinate like before, then no matter what angle this Cn rotates, so suppose I rotate by 60 degree or 120 degree or any amount of degree, the z coordinate for this particular point is not going to change. The value of z will remain same, and it will be on the positive side of this z axis all the time, right? So after I have operated Cnz on this particular point, it will be something like point, say P prime, where this x be x prime, y be y prime, but z will remain z. Okay. So if I have to find out the matrix, I can always say that, okay, I do not know about the x and y part, but the z part will be having an element which is unity, like what is shown here on the screen. So I do not know what are the elements that are going to be here, because I do not know what are my x prime and y prime, but I know for sure that z remains z. So that will have this this 001 and 001 here, correct? That will not change my z. Now we have to find out what will be the fate for x and y after I give a rotation. So our idea will be to find out most general form of matrix representation by which I can get a matrix form for any given Cn. N can be 2, 3, 4, whatever, but I should be able to do that. So let's try to do that. So suppose we have a point in the xy plane whose coordinates are x1 and y1. That's what is shown in this particular diagram. So I have this particular point to start with. Okay, so this point is described by a vector r1, and this r1 traverses the distance from this particular point to the origin, right? Now suppose that this vector is rotated. Okay, so I give a rotation like this, and the angle of rotation is theta. Okay, so that we get a new vector whose vector, the corresponding radial vector is r2, and the new points are x2, y2. So with that setup, we will try to inquire about how the final coordinates x2 and y2 are related to the original coordinates x1 and y1, and also the angle theta. So we can work this out. So how? So when x component of r1 x1 means x component of r1 is the x1 actually is rotated by theta, it becomes a vector, say x prime, which has an x component of x1 cos theta and a y component of x1 sin theta. This is a simple geometry problem, so you can easily find that out. And similarly, we can have the y component of r1, say y1. When we rotate it by theta, it becomes a new vector with new vector y prime, which has an x component of minus y1 cos theta and a y component of y1 cos theta. Now x2 and y2, the components of r2, which is a new vector, must be equal to the, this is very important, right? This must be the equal to the sum of x and y components of this x prime and y prime. So thereby we can write these two equations that is given here. So equation 1 and equation 2. So here one thing I will mention, all these 2's are supposed to be subscripts. Okay, for some reason it's coming as such. So you can correct this one, and you can write like this is x subscript 1 or y subscript 1. Okay, but that will not make any change to the context at all. Now once you have written down this equation, you can find out the transformation matrix, because your aim is to find out what happens. I mean, what is this x2, what is the y2. Now you have found out the x2 in terms of x1, y1 and the theta, and you have found out also about the y2. So now if you couple these two equations, you can very easily find out the matrix for that. So the matrix form that you will be find out if you utilize this two equation is here. So originally you had x1 y1 as your column vector, now you have x2 y2, and this is the matrix which you have to apply on this xy y1 column vector, so that you get x2 y2 column vector, right? So in a sense, this 2 by 2 matrix that is on your screen here, that represents the empty space that was left when we started forming the matrix for Cn in general. Like we got the values for the z coordinate transformation, but we didn't get for the x and y. Now this 2 by 2 matrix will fill that gap here. So if we do that all together, what we get is here. Now one thing one has to be very careful about, what is the orientation of your rotation. Okay, it can be either clockwise or counterclockwise. So whatever we did, we rotated in this fashion, right? If we just go back here, we went from x1 y1 to x2 y2, which is counterclockwise, right? So all our derivation is based on so far a counterclockwise rotation. Now if we want to do it for a clockwise rotation, that is very easy, because cos theta equals to cos theta and cos minus theta are same, while sin minus theta is minus sin theta. So utilizing that we can find out the 2 by 2 matrix for a clockwise rotation as well, which is shown here. Now finally we can write the overall clockwise rotation overall matrix for clockwise rotation by this expression. Now the beauty of this matrix in terms of this angles phi or theta, whatever you use, is that you just give the value of that particular angle. If it is C6, then you give 60 degree. If it is C2, you give 180 degree, and you get the corresponding value for cos or sin phi's, and you get the matrix. All right, and that matrix will act upon this xy x1 y1 z1 column vector and ultimately give you the final result. Okay, so you can figure it out yourself that what will be the form of the matrix for any given Cn, C3, C4, C5, whatever you can think of. You can try those values and get the matrix forms. Okay. Now we are left with the last one, that is the improper rotation. Now it should be straightforward for you by now. The reason is we have learnt about the proper rotation, we have learnt about the reflection. So improper rotation is nothing but rotation followed by a reflection. So in case of proper rotation, we have a matrix like this, right? This is my proper rotation barring this one. Okay. So for a second, if you think that okay, there is no minus here, so this is the matrix for my proper rotation. Now in case of improper rotation, you rotate, so you rotate by an angle and you use this matrix and get the matrix form for that one. Now after this rotation, you have to get a reflection on the perpendicular plane, so you know exactly which is the plane. So first you rotate around z and then you reflect around xy plane. So when you have sigma xy, what is that coordinate which changes is the z. So the z will be minus z, correct, after you get that reflection. So you have the rotational component here, and this component with this negative sign is for the reflection on xy plane, and exactly that's what is the overall matrix representation of improper rotation. Okay, so we will we can go ahead and in general we can find the matrices that describe symmetry operations, and we can verify that this matrices which are representing the symmetry operations, they are equally capable of doing the successive operations. That if this multiplication of two matrices corresponding to two symmetry operations will generate a matrix for another symmetry operations. Okay. So if suppose I have like sigma xy, sigma xz and sigma yz successively, then I am supposed to get C2. Now if we take the matrix forms of sigma xz and sigma yz and do the multiplication, then I will end up getting a matrix representation which actually gives me C2z, actually gives me the matrix representation of C2z. So this matrix multiplication can satisfy the successive operations of this symmetry operations. So the bottom line is we see here that this matrix algebra can very well represent the symmetry operations of any given particular point group, and we showed by showed very generally that this holds good, and you can take any specific point also and form their own matrices and verify this whole process that we have gone through today. So we will stop here today, and the next week when we come back, we will look at in a greater detail about the how to form the representation of a group as a whole. Okay, so till then I will leave you with this, and I will request you to practice a little bit more about the matrix, how to form the matrix representations of symmetry operations. So thank you for your attention. See you next week.